This is Lab 4, the physics of extreme sports with ropes. The purpose of this lab was to analyze the motion of a mass oscillating on a spring using the energy principle and Newton's second law, and to compare our model's positions and energy curves to our data's. Overall, I found the change in energy was constant and zero, satisfying the energy principle, and the model and actual data's change in position were similar, but with obvious discrepancies. Newton's second law gives us the ability to analyze and predict the motion of an object. In general, force is equal to mass times acceleration. Starting with the position data of our mass on a spring, we can calculate the velocity of the mass at each time step. In this case, we have a non-zero force acting upon the mass, so acceleration is also non-zero, and therefore velocity and position are changing. Another important principle in this lab is the energy principle. This states that energy cannot be created nor destroyed. Therefore, the change in energy will be zero, since the energy only transfers between kinetic and potential energy. Kinetic energy, 1/2 mv squared, occurs when the object has non-zero velocity. In addition, potential energy of the spring, 1/2 times the spring stiffness times the change in length squared, and gravity affect the system. Mass times the gravity constant times the change in y. In my model, I set a few key initial conditions like mass, position, and velocity. Velocity was calculated as the average velocity from rest in the first time step. To compare the model to our data, I first graphed the predicted and actual y positions. I found that the positions did not line up too well. I altered my initial velocity and time step many times, but unfortunately no change made the matching noticeably better. The slope and oscillation periods seemed to be very close, but positions were not perfect. This could be because of human error with calculations or coding, or it could be due to our system not being a perfect model with other forces applying to it. When we plot the changes in energy, however, the graph models this quite well. The blue curve represents change in kinetic energy, the red curve represents change in potential energy of the spring, the green curve the change in gravitational potential energy, and the yellow the change in total energy. As you can see, the potential energies are quite large and opposite of each other. Kinetic energy is small because velocity is small. Most importantly, though, is the yellow total change in energy curve. The curve has a zero slope and is equal to zero, satisfying the energy principle that change in energy should be zero because energy is neither created nor destroyed, only transferred. An important factor with spring oscillation is the time period of each oscillation and the amplitude. As a general trend for the x position periods, oscillation period and amplitude decrease a good bit from each period to each period. The first oscillation period is about 1.7 seconds in length, and the third one is only about 1.2 seconds in length. In addition, amplitude decreases about 0.5 meters from beginning to end. For the y graph, oscillation period appears to slightly increase while amplitude decreases. This occurs because we have a non-perfect system. In the model, only force of gravity and the spring are calculated, but in reality other forces like drag affect the mass. This slows the motion of the mass and causes less oscillation of the spring. Overall, we find that using Newton's second law and the energy principle helps us predict an object's motion. With oscillation of a spring, the spring itself makes a large difference in the potential motion. We can use these basic physics problems to understand extreme rope sports and enjoy the spectacle in front of us.